So maybe we can start now. Welcome to the live session uh, for week 11 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dikshit from IIT Kharagpur. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving some of the assignment problems that have been given to you in the week 11 assignment. So we have almost come to the end of this course. As you can see, we have already covered all the device physics and most of the important models that we have that are made basically to realize the semiconductor device using some simulations. So uh, in the first week, if you remember, we talked about this device scaling and nanoelectronics, etc. And we did discuss that the device limit has reached to very few nanometers now. If you see the latest, I mean, in the latest IEDM conference, there was an announcement that there will be commercialized ribbon fed by Intel, which is around 3 nanometers. So it is very difficult to model these, and as you know that the what I can say that the radius of atom is even around some few angstrom. So it is very close that we have only few atoms in the channel, because even for a 3 nanometer node the channel will be very smaller. So, so because of that, there are various quantum transport that is happening. So, what is happening that the model is sorry, not the model. The electrons are not since their length is very short, they are behaving like a quantum particle instead of having some classical physics, in which in the initial part we studied that some electron can act like a particle, but it also have some effective mass. So that is what these models are relating to. So in this particular week, we'll again be covering. So in the initial weeks, I did cover some of the Schrodinger part. So we'll see that again. So the basic quantum transport model revolves around the Schrodinger equation only, and there are few different types of Schrodinger solutions, that is for infinite well and finite potential well. So we'll quickly see those, and then there is this potential barrier. So this is all comes under the Schrodinger part only. Yes, any doubt? Oh, yeah. And then there is this matrix approach and quantum mechanical correction. So these are all again the complex quantum functions, such as, if you might have heard, that is a non-equilibrium Green function. So to to have more complex, I mean, for more complex structure, the transport can be either ballistic transport, or it can be non-ballistic. So for that, we require a lot of different types of models. So I mean, ballistic transport is not the part of this course. So the Schrodinger is only the part. So we'll quickly see what is the Schrodinger equation and what is the wave function and all. And yeah, I will try to cover some of the problems that are related to this, and then yeah, we might conclude the today's week. So let me quickly introduce you with the wave function. So does anyone know what is the wave function? I mean, I did kind of covered it in, I mean, some of the initial lectures. I don't know which lecture. Okay. So as you know that electron, yes. Okay. Okay. Yeah. Kind of that. So the probability of finding an electron in the quantum state is this. I mean, it is related to wave function, but that exactly is wave function square. So yeah, I mean, it is somehow interrelated to the finding the probability only. So yeah, let me give you some more uh, focused definition. So we know that the electron behave like a particle as well as a wave, right? So we can say that it is kind of a wave particle, and we want to now model it because we are talking about this modeling. And a convenient way to model this wave function, to do this is using the wave function. So this is kind of a modeling technique to have the quantum transport, and this wave function is purely a mathematical identity or entity. It is purely mathematical. So wave function contains what it contains. It contains all the information of the particle. So by all the information, I can say that it also contains particles, energy, It contains momentum, and it also contains the wavelength, etc. I mean, all the quantities. It can be kinetic energy, it can be the total energy, etc. And then there is a scientist named Bond who said that the significance of the wave function is that its amplitude squared. As Nilesh said, that its amplitude square represents the probability of finding an electron. Yeah, and this is per unit volume to be precise. And there are few properties of the wave function that it goes through with. So some of the properties of the wave function you might be already knowing. So any guesses? Anyone if they want to tell? Otherwise, fine, no problem. So first of all, the wave function must be a solution to the Schrodinger equation. Give me a second, guys. Yeah. So wave function must be a solution to the Schrodinger equation. Then, as it is a solution, so the wave function must be continuous. And the third part is wave function must be differentiable. That basically means that d phi by dx should exist, right? Or this also we can write that we can also write that d psi by dx should exist, or this must be continuous. Then the last is it must be normalizable. So as it is kind of a probability, so it should be normalizable. So in mathematical terms, what I can say is in the entire space, the probability of finding a wave function should always be equals to 1. It cannot go beyond 1 and it cannot. So basically, what it means is if I, let's say, for example, if I try to say that wave function is, let's say, e raised to power x. So can anyone tell if e raised to power x is, sorry, normalizable? It can be normalized. Okay, there is a lot of noise. Yeah, I'm saying that it should be normalizable. That means that at all the current existing space, the probability of finding the electron should only be 1. It cannot be greater than that of 1. So what I was asking is, if I take, let's say, a wave function of e raised to power x, so can I take this wave function? Any guesses or any idea? Okay, why? Why do you think that e raised to power x can be a wave function? Okay, okay, fine. So we have taken, let's say, e raised to power x. So what if I say that if x tends to infinity, where will be the wave function tends to? So can we take the wave function? Yeah, the sum of the entire wave function or the probability should always be equals to 1. So e raised to power x cannot be a wave function. That is what I meant by normalizable, that it should not blow up. So this condition is basically realized by noting that the particle must exist somewhere in all the allowed region and the total probability is always 1. So basically we cannot take e raised to power x as a wave function. So you might have got confused if you have read that it does look similar like that, but we cannot take e raised to power x as a wave function. Now there are several quantum operators that we should know before going towards the Schrodinger equation. So let's say we have a wave function psi, which is given by e raised to power j. So j is a iota that is the imaginary under root minus 1. I hope you know this. Let's say, yeah, it is a function of initially position as well as time. So there are few quantum operators. So there k is a wave number which is 2 pi by lambda, and this omega is a frequency which is 2 pi nu. So there are few quantum operators. So first is the momentum operator. So momentum operator is nothing but, so momentum is denoted by P, so it is H cross by J, so J is again the iota and del by del X. So momentum operator is a function of position. Similarly, we have energy operator. Energy operator is denoted by E, and energy is basically a function of the time. So H cross minus H cross by J, it is d by dt. So T is the time here. Or if there is another expression to this, you can change it. So if you multiply it by psi on both the side, it is nothing but d psi by dt. So I mean this is a way to solve. So yeah, so let me, as I said that this is a wave function, right? Where is that? Yeah. So can anyone tell what will be the momentum operator? You just need to uh, differentiate it with respect to x, and for the energy operator, you need to differentiate it with respect to time. Do you understand what I'm trying to ask? Yeah, just quickly let me know what. Yes, yes. Okay. J. Okay, let me write what you're saying. So for momentum, you're saying it will be, yeah, yeah, yeah. E to the power e to the power j. Jkx. This is what you're saying. Can anyone else? So, okay. Anyone else? Okay. So since we are dealing with the position here, so this will also be a constant. So it will be jkx minus omega t. Yeah, just to give you example, so ex plus a, the differentiation of ex plus a is nothing but ex plus a only. So this is like that only. So, and this whole term is again psi, right? Yeah. So hk is the momentum operator. So what we write is pxi. Then similarly for energy, we just need to differentiate it with respect to time. So if you will try to do it, it will come out to be h omega. Sorry, k. Yeah. So it will be same. So minus will cancel out. So again, so it will be something h nu or h omega, that is e psi, that is equals to e psi, because this particular term is psi. Then similarly, we have a kinetic energy operator. Let me just tell you what is it, and then we can move forward. So the kinetic energy, I mean, it does come from somewhere. So we know that the general notation is half mv square, which is also p square by 2m. And if I write 1 by 2, so p square, we can take the momentum operator twice because it is p square. So it was h by j d by dx, and then the second is again h by j d by dx. So I've squared, due to the p squared, I've double differentiated it, and if you just try to solve it, it will come out to be minus h square by 2m and d2 psi by dx2. So this is the energy operator or the kinetic energy operator, not the energy operator. I hope it makes sense. So if it do make sense, sorry, yes, yes, this fine. So now what we'll see is the Schrodinger wave equation. So does anyone already know what is Schrodinger wave equation? Okay, fine, no problem. So we know that in classical physics or the classical equation, yes, yes, will be zero. The fine, fine, no problem. So we know that the classical equation for energy of a particle is that we know that the kinetic energy plus the potential energy is the total energy, right? Not zero, but the total energy. So this total energy, I mean, if I try to write classically, it is p square by 2m plus the potential energy, which I'm denoting with v, is the total energy. This is how we write in the classical physics. But in Schrodinger, sorry, but in quantum physics, what we have is we have the operators wave function, as I said. So for these variables, the operator are allowed to have a wave function, which is given by this Schrodinger equation, which is nothing but minus h square by 2m d2 psi by dx2. This is nothing but the kinetic energy operator I just told you in the above equation, plus v psi is equals to e psi. Make sense? Okay, sorry, not plus v psi is equals to the energy operator was, if I try to write that also, it was minus h by j d psi by dt. So this is the energy operator, this is the kinetic energy operator which I told here. So this is kinetic energy, and yeah, where is that energy operator? Yeah, this is the energy operator. So this is what I wrote here. Is it fine? Yeah, so this is for one direction. Similarly, we can write it for two direction or three directions. So I mean, in general, we can write it as minus h square by 2m. So we denote the delta using this triangle shape, which can be applicable for any dimension, plus v psi. So it is kind of a matrix form, minus h by j d psi by dt. So we can say for 3D it is like that. Now this is, as I said, this is the potential energy part, right? So it depends upon the potential profile in which the electron is placed. And here this del 2, if you want to have explanation, so this is nothing but the x direction plus the y direction plus the z direction. You can have any directions, but yeah, for 3D specifically, it will be 3. So the wave function in the above equation includes both space and time. You see, it is time also dependent, and it is, where is that? Yeah, it is also position dependent. So it is very common to calculate these dependency and combine them later. So initially what we'll do is, because it is very complex to do, initially what we'll do is we'll try to solve the time independent Schrodinger equation, which is this part will be, there will be no dependence upon the time. So I'll just replace that part. So let me try to do that. So we have the time independent Schrodinger equation, which will be nothing but it will remain same because we have the time dependency. So x will be there plus v psi, which is the potential energy, and is equals to e psi, which is the total energy. And similarly for 3D, we can just replace it with delta. So I'm not doing that. So the for the first case, I'm considering, as we said, as we know that the potential profile is depending upon the where the potential is, or where the electron is placed at. So I'll be taking the first case, which is the infinite potential well, or infinite barrier potential well. Also, people say it. I'll tell you why. And also, this is the 1D case, not the 3D one. Yeah. So let's consider a electron. So we have kind of a well, and the barrier of this well is around infinity. So that is why it is called infinite potential barrier well. So the electron will go through somewhere in between from this well. So let's say this is at x equals to 0, this is x equals to L. So the length of this well will be L. And what we can say is outside this, there can be no electron, and yeah, outside this means both the sides, there could not be an electron, and inside this, there is a wave function which exists, which is not equals to 0. And the potential that we are starting with is exactly 0. Give me a moment. Yeah. Yes. So yeah, what I was saying is, so this is, let's say, Vx, that is the potential energy part. So it is infinite at outside the well, and it is 0 at inside the well. So this is the case of the infinite potential barrier well, and we'll try to solve the Schrodinger equation for the same. So as you can see, this the electron cannot escape it because it would need an infinite potential energy to escape this particular well. So it is not possible practically, and the probability of finding an electron per unit volume will be, what will be, it will be 0 at outside the well, and it will be, the total probability will be 1 inside the well. So what I can say is, at x less than equals to 0 and at x greater than equals to L, psi will always be 0. And inside that, we have considered the potential to be 0. So using this, we'll just solve the above equation, which is this. So we'll feed all the values that we have. So yeah, let's try to do that. So it is minus square by 2m d2 psi by dx2 plus v psi is equals to e psi. It was this, right? So inside the box, what I told you that the potential is 0. So this term will go away, right? So it will be minus x square by 2m d2 psi by dx2 will be equals to e psi. Any doubt in this? So sorry, v psi, no. I have told you that the potential inside the well is 0. So this is a plot. Yeah, out. So the electron cannot go through cross this barrier because the potential is infinity. Yeah. So the electron will be inside only, and inside the potential is 0. I've taken the potential to be 0. Yeah. So if I just make this d2 psi by dx2, and this 2m and by h square will come here. So 2m by h square psi. So like there is a variable that we replace it with. So the under root of 2me by h square is equals to, I can write this m as p square by 2m by h square. So m and m will cancel out, I mean 2m and 2m. So this 2me by h square is what we also call as p by h, and this is what we also call as k. So I mean this term is basically k square because the under root is that. Just to simplify the equation, I'm writing like that. So this d2 psi by dx2 is minus k square psi. So this is a basic differential equation that can be solved. So does anyone know what is the general solution to this? It is very easy. Okay, no, so there is a psi here. It is not straightforward. The psi will come here and then x will go there. So okay, no problem. So the general solution for this equation is, it is nothing but psi x, psi x is a sine kx plus b cos kx. So try to differentiate it twice, you will get the same thing. Uh, do anyone wants to do that, or I just move ahead? Okay, so if, so there is no like very hard thing in this. If you differentiate it twice, you will get the same thing. Yeah, so what we know is, so now we need to find the constant. So we know that at x equals to 0, the wave function is 0, and at x equals to L, the wave function is 0. These are the two boundary conditions that we know. So let's put it one by one. So at x equals to 0, psi is equals to 0, so it will be a sine 0, that is 0, plus b cos 0, that is 1. So this will make b is equals to 0, right? So now psi x is a sin kx. That is what we left with. Now we'll apply this boundary condition to find the value of a. So let's try that. So at x is equals to L, what is psi is equals to 0, and we have a sine kl. So what will be the general solution to this? What will be the value of k or kl, not even k? To make it 0, what? Yeah, that is one value. I mean, in general, so sine n pi 0, right? There is no single value. Yeah. So kl will be equals to n pi. That will make the value of k. Okay, so we'll first find k, that is n pi by l. From this, we came to know that the wave function is a sine n pi x by l. We still need to find a. So can anyone tell how can we find a? Let me give you a hint. So there are four properties. Hmm, can anyone guess how can we find the a? Yeah. So normalizable property we are left with, so we'll do that. So the total probability inside the well, we know that it is zero outside, right? So only 0 to L will matter. So what I'll do is, I'll make integration from 0 to L, because minus infinity to infinity, rest is 0. Del x square, oh sorry, psi x square dx will be 1. So I'll just try it out. You also try it out from your end, all of you, and let me know what is the value of a that you are getting. So it is 0 to L. So square will be a square sine square n pi x by L is equals to 1. Sorry, dx. So do all of you remember how to do integration? What is the integration of sine square x? Anyone? Yes. Yeah. Yeah, so this will be 1 minus cos 2x, so 2 n pi x by L by 2 also, so I'm writing this 2 here. Dx is equals to, sorry, into dx is equals to 1, yeah. So if I now try to integrate, so the integration of 1 will be x minus the integration of, what is this? Yeah, cos 2 pi, yeah, so it will be sine some constant, let me write k only because it will cancel out later. It will be sine 2 n pi x by L, and the limit will be 0 to L. So if I put L in this, so L and L will cancel out. What will be sine 2 n pi? Yeah, and sine 0 will also be 0. So right, this part will go away. Understood? Yeah, so only limit is left with this, that is 0 to L is equals to 1. So what I can write is a square by 2 times L is equals to 1. That makes a is equals to under root 2 by L. Any doubts in this? So we were here. So the final wave function looks like root 2 by L sine n pi x by L. So this is the solution to the wave function for a particle in an infinite potential barrier, or you can also call it as sorry, 1D box. Similarly, if you want it for three dimensions, I mean the solution will be same. Let me just quickly tell you that also. So it will be Lx also, Ly, similarly Lz, and similarly it will be sine n pi x. So I hope you understand what I'm trying to say. So I'm not doing that. So this is the solution. Now the main thing that we want for a particle that we want to know is the energy of that particle. So we have got to know what is the wave function. So we'll try to find the energy. So let's try to find out the kinetic energy. Oh, sorry, not the kinetic. So we made this assumption that this k is 2 me by h square, right? Which was n pi by L. So if I try to do it, so this will be 2 me by h square, sorry, h cross square is equal to n square pi square L. This will give me energy as n square pi square h cross square by 2 ml square. And we can write this also as h by 2 pi. So it will be n square, so 2 pi will cancel out, and 4 to the 8. So it will be n square h square by 8 ml square if I'm not wrong. Is it correct? So h cross is basically h by 2 pi. Yeah. So this is the energy of the particle. So can you comment on the energy of the particle by seeing this current formulation? Is it continuous? Okay. So you see here the energy. Yeah, it is discrete. So the energy of the particle is quantized that I mean, what to say, every formulation says that energy is discrete, like it only exists in certain energy levels. So the energy of the particle is still quantized in the quantum mechanics. And what I can say is if the energy, sorry, if the length, if we increase the length of the box, that is, if we increase the width of the well, what will happen? The energy will decrease. And similarly, if the mass will increase, similarly, the energy will decrease. So what it means is as L is increasing to, let's say, macroscopic dimensions or a very high L, the electron is completely free and the energy of the particle becomes continuous. Make sense? Because if L is very high, then N does not make any sense. So basically what I'm trying to say, as L tends to infinity, E is trying to become continuous. There will be no discrete levels left. Make sense? Yeah, yeah. So if L is very high, then there is no discreteness. That is what I'm trying to say. I'm not saying to keep it infinity. I'm trying to say this: if L is very high, energy will be continuous. I mean, that is what we study in the classical physics. But in what to say? But in quantum physics, this L is very small, right? In the few nanometer regime. So that is why energy is decreased or energy is quantized. I hope it makes sense. Yeah. Yes. Hmm. It can. Uh, it can. I cannot hear what are you saying after it can. No, no. Oh, if L is large, we know that if L is large, there is this classical physics, right? Kinetic energy plus potential energy is total energy, that is E square by 2m plus V is equals to E. We don't need to do any quantum operator. We don't need to apply the Schrodinger equation if we are doing with the classical physics or dealing with the classical physics. Yeah, this particular thing is only for the quantum mechanics. Yeah. So let's try to see some of the problems. I mean, there are straight away very easy problems for this particular lecture. So it says consider an electron in the 1D infinite potential well, that is what we just derived of the width L and edges at x equals to 0 and L. So this is what the same calculation that we did. So it says calculate the probability of electron to be present in between x equals to 0 and x equals to L by 4 and assume n equals to 1. Yeah, so this is a good question, I mean. So you all give it a try and let me know. You can take 2 minutes or 5 minutes also. That will be good. Just try to give the answer. Is it fine? Yeah. Uh, any solution? Okay, so it says that we need to find the probability in between 0 to L. How can we do that first of all? I mean, what exactly do we need to calculate? Can anyone tell? Yes. Yeah, this is the probability, right? This is what we need to calculate. Oh, sorry, from 0 to L by 4 it is saying. Yeah, and we already know the solution, what is psi square, and yeah, we just need to keep the value, and it is already given that it is 1, so let me do that. So it will be 2 by L, that is the square, and sine n pi x by L. So it will be square, so it will be from 0 to L by 4, right? So we'll again apply the same thing, 1 minus 1 by 2, so it will be 1 by 2 minus cos 2 pi x by L. Okay, it is also by 2. So let me write 1 by 2 outside only. So this and 1 by 2. So 2 and 2 will cancel out, and the limit is 0 to L. Sorry, I'm not integrated it yet. Integration dx. Oops, sorry. Yeah. So it will be 1 by L. Then the integration is x minus sine 2 pi x by L, and there will be L by 2 pi outside, right? And then the limit is 0 to L. So it will be 1 by L, oh sorry, L by 4. So the first term will be L by 4 only if I keep the limit. The second term, if I keep here L by 4, it will be L and L will cancel out. So it will become pi by 2, right? So it will be minus L by 2 pi, if I'm not wrong. Then 0, it will be 0 and 0, yeah. Makes sense? Have I done it correctly? L will cancel out something. In, yeah, x will, I keep the limit, right? So x will be changed to L by 4 first and then 0. So if I, yeah, so if I keep x as L by 4, so this is this, and L by 4 means, so this sine 2 pi x will be L by 4 divided by L. So that will become sine pi by 2, and this is 1. So if this is 1, then it will be L by 2 pi only. And for 0, both the cases it is 0. Sine 0 is 0 and x 0 is 0. So L will cancel out, it will become 1 by 4 minus 1 by 2 pi. Can anyone use the calculator and let me know what is the answer? So 1 by 4 minus something, so this cannot be the answer. Please, okay, let me also use the calculator if I can. So 1 divided by 2 pi. Yes, it cannot be minus. It is 2 pi. Probability cannot be negative. 2 divided by pi minus. What? 0.090. There are option. Yeah, so there is option. So option C is the correct answer. I hope the calculations is correct. I don't know. It will be something like this only. So 0.09 is the answer. Is it fine? Yeah. So now again straight away question. Let me know the answer quickly. Okay, yeah, it says not or satisfied. It should not be discontinuous. It must have multiple, so it cannot have multiple values. Must have abrupt change. So yeah, C is the correct answer. Very easy. And this also, let me know quickly. Wait. Okay. Okay. It says identify the incorrect statement. Yeah. This should not be zero. This should be continuous only. Because if the slope is zero, then basically psi is constant, right? It is not. It is a function of position or time. Makes sense. So it should be continuous. It should be a single valued, and yeah. So incorrect is A. Yeah. Since again is some mathematics problem. So it says wave function of electron is shown like something like this. If x is in nanometer, c is a constant, then c is equals to. Yeah, this is a good question, I guess. So do you want to try it? Yeah, sure. Yeah, okay, yeah, go ahead. Please let me know how you're approaching the problem. Okay. Yes. Yes, yes. Yeah, you need to do it something like that only. Yes. It's not that large. Let me also do. Nilesh, so have you done that? No, no, root 2 is not the answer. That is what I know. No, no. Answer is something 3 point something. That is what I know. I also don't know. Yeah, yeah. Yeah, just we can check quickly. So it is C, and then it is e raised to power minus 2x. That is a square. And minus e minus x square dx is equals to 1. So basically, I can write 1 by c is equals to this thing, that is 0 to infinity e raised to power minus 2x. Okay, I need to open this. This is 1 plus e raised to power minus 2x, and it will be minus 2 e raised to power minus x. Please let me know if I'm doing anything wrong. I also don't know. So this is 0 to infinity e raised to power minus 2x plus e raised to power minus 4x minus 2 e raised to power minus 3x is equals to 1 by c dx. Sorry. So which is okay. So it will be minus 1 by 2 e raised to power minus 2x minus 1 by 4 e raised to power minus 4x, and this will become plus 2 by 3 e raised to power minus 3x, and the limits are from 0 to infinity is equals to 1 by c. So infinity, okay, e raised to power minus infinity is 0, right? Yeah, so it will be minus 1 by 2 minus 1 by 4 plus 2 by 3 is equals to 1 by c. So, okay, it's minus 3 by 4, 2 by 3 minus. Oh, yeah, yeah, yeah. Yeah, 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 I get it. Yes. So it is. Oops. Is it coming negative? Oh, no, no. 3 by 4 minus. Oh, no. Y square. Acha, it is square. Okay, okay. Yeah, yeah. It is square everywhere. So it is basically 3 by 4 minus 2 by 3. So it is 12, 3, 3, 9, 3 for the 1 by 12 basically. So c square, 1 by c square is 1 by 12, right? And that makes c square is 12. I don't know what. Yeah, so c is under root 12, right? Which will give 3 point something. Yeah, 3 point. What is the answer? 3.46. Okay. The answer is, yeah, yeah. So it is 3 point. Okay, yeah, fine. Fine. Shall we move ahead? Yeah. So again, a simple question. So what is the least amount of energy that a particle can have in an infinite potential well? The width is given. Oh, this is very easy. Quickly let me know the answer. This is, I mean, very easy. We just need to use the energy formula that we derived. Should I wait for 2 minutes, right? Uh, is n square h square by 8 ml square. Oh, you also need these values. So this is 6.626 minus 34, and m is already given. Okay, okay, sorry, nothing. Just take 2 minutes and then I'll also solve it. Sorry? Oh, sorry? Hmm. No, no, by least means the lowest energy level. So it will be just h square by 8 ml square. You know everything. So 6.626 square minus 68 divided by 8 ml. M is given. Yeah, it is 9.1 minus 31. L is also given, I guess. Width is 10 nanometer. That means 10 to the power minus 8 square is 16. And this is in joule, so to convert that into electron volt, it is 1.6 minus 19. So this will be the answer. I mean, I don't know what it will. Okay, let me check. So it is 47 and then 67, 66. Yeah. So this will be 10 minus 2 if I'm not wrong. Then, okay, let me use calculator. So it is 6.62. You can also use calculator. I don't know. 6.62. 0.439, okay, 0.439 divided by 8 divided by 9.1 divided by 1.4. I'm getting very low, I don't know. Okay, you try. I'm getting one answer, but that is quite low. I, sorry, 6 point? No, no, tell me electron will divide by this number also. Yes. Okay, this is what you're getting. Okay, so, and yeah, 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 yeah. So that answer that you got was in joules, so I've divided it by extra q to convert it into electron volt. Sorry. So this is 1.6 by minus 19. So this is the electronic charge q. So this formula gives you energy in joules. If you divide it by q, it will be in electron volts. So are you getting this only right? I'm not sure. You just divide your answer by this, you will get the same, I guess. What I got was 0.00376. I don't know. Okay. So I did get 376, but my decimal place was something else. That is why I'm confused. Did I write something wrong? 10 nanometer is minus 8 square 16. Yeah, so the other person is getting the same, right? 0.376 is fine. Okay, I'm assuming it is correct. You can redo the calculation, I mean, it is straightforward. Okay, again, the most general solution. Yeah, we just did. What is the answer? Yeah. Then it says the Heisenberg uncertainty principle. So yeah, we have also covered that. What is the answer? B, right? Yeah. So it states that we cannot govern the position as well as the momentum at the same time. So yeah, I mean these are some of the basic questions. So what I want to tell you now is that this is the solution of the Schrodinger equation. I mean we only did it for the infinite potential well. So there are three more cases. I mean, they're very complex. So there is a case for finite potential well, in which what we do is we take the same case, but the V here is V naught. Instead of infinity, it is V naught. So it makes the solution or the equation very tough. I mean, this is a long equation. So yeah. And then there is one more thing, which is a coupled well. So we repeat it by two times. And from this only, it leads to the discretization of band diagrams. I mean, it is very complex. I'm just letting you know from where it all comes from. And using the Schrodinger equation only, we calculate this density of states. So do you remember density of states? Let me, if you don't, let me try to remember, make you. So it is something like some constant, which is even better. So this is the density of states for a, I guess, for a 2D or a 3D case. Yeah, for a 3D case. So this also comes from the solution of the Schrodinger equation only. And I mean, if you remember, we make the diagram like this. In some other class, I must have told you that this is the density of states above EC and above EV. It looks like this. And this is what I just wrote. So if EZ is E minus EC, then it is this formula. And if E is EV minus E, then this is this formula. I mean, this is straightforward only. I'm just letting you know that all of this also comes from this. So, any doubts in the Schrodinger equation part? I mean, this is most of the thing. Okay, yeah. So, yeah, so this is mostly all I have. The most basic thing is to have the idea of this Schrodinger equation and the operators. So, yeah, one thing is this operators also. I mean, there could be few problems that can be made from these. Let me see if I have some. Uh, I need to check. I'm checking. Okay, no easy problem in this. Yeah, so I have got one problem. Let's do that also quickly. This is a good problem. I guess this is also in the assignment. So what we have is question is, so we have the potential energy. Okay, no, we don't have. So the wave function of the particle is given. It is ax exponential of minus x square by L square. So yeah, and the particle is having mass m and zero energy. And this has a time independent wave function where this A L and are constant. So the question is determine the potential energy. Does the question make sense? So we need to find the ux basically. Any doubts in the question? Yeah, just try it out. Yes, yes. So basically you need to differentiate it twice. I mean, so this is the equation that is d2 say plus ux psi x is equals to e. So that is 0. So, so ux multiplied by this ax ex by L square is equals to minus h square by 2m, the double differentiation of this thing. So let me write for now like this ix. Yeah. So did you do the double differentiation? Sorry. X square by L square. So this will be equals to x square by 2m will be constant. So it will be a is again constant. So I'm taking a outside. So x, let's keep it as it is. So it will be e minus x square by L square, then 2x, oh, minus also, and then minus, so it is minus 2x square plus, let's do the x, so it will be e minus x square by L square. X remains the same. Yeah, is it correct? And yeah, I hope so. So this a will go away. E minus x square L square will go away. What we are left with is, okay, let me check. The first time, okay. So what are you saying? It will be 3. Where? Here. No, there was cube or yeah, by L square I forget. Yeah, by L square I forget. X square. So you are saying this is 3. How? So differentiation of this x square is 2x. That is what I wrote. Where is x cube? Where is it? Okay. So, okay. Sorry. I have done it only once. Yes. Yeah, sorry. So yeah, I cannot cancel anything yet. So x minus yeah. So double differentiation is also remaining. So what I wrote was, let me rewrite that. So it was something like, I don't know, minus. So the double differentiation will be, okay, it will be a long term again. So minus 2 L square. X will be as it is. Then how come? Where is the cube? I'm not sure. So it is again 2. Uh, hmm. Yes. Hmm. Yes. So this is what I did. Yes. So x, if I leave as it is, so the differentiation of this is this. That is e minus x square by L square will be minus 1 by L square, e minus x square by L square, and this term will be minus 2x. So this will become plus. And if I leave this as it is, so x will be 1. And then if I differentiate it again, so it will be 2x by L square. Let's say it is as it is. So I don't know. I only know the last step. Let me write that. Please also let me know if you get it. So it is 2h square by m L is for 4 x square minus 3l square by 2. This is what it is coming. I don't know how for now, but this is the last. Yeah, you will check maybe. Yeah, if you don't get, you can let me know in the next lecture. So this ux, you need to find it x equals to 0. Sorry, I forgot to give it, I guess, at x equals to 0. So if you keep x equals to 0, so the u at 0 will come out to be 0. Okay, h square by minus 3 and 2 ml square, I guess. Yeah, something like that. Make sense? Just recheck this. I mean, the double differentiation. Yeah, you can use some online tool. I don't know exactly what I'm doing. Is it fine? Yeah. Let me just stop the recording.